we have one last section to look at in this unit about exponential and logarithmic functions. And that's section 5.5, but before we get into there, there's a topic we have to talk about called logarithmic differentiation. Your book does it in a couple different sections. We're just gonna do this. Mr. Alberts? Yeah, we're down. We got nothing. We got no internet. We're done. The people at home, I told them to sign off. Just FYI, since you put your 10-minute speech into the school committee this morning about the internet, just figured you'd want to know.
Well, it would be terribly awkward if I went on an internet rant and then the internet was perfect today, so I guess maybe.
Yes.
But hey, it's good.
Oh, and I just recorded all that. Wonderful. Okay, well, here we are. Y equals x to the 2x, I want to find dy dx. Here's the deal. Number one, power rule only works if the power is a constant, and it's not. Power rule only works if the power is a constant. So I can't use power. Can't pull down the power, subtract 1 from the power. My e to the x rule only works if the base is e. By the end of today, we'll see what to do if the base is 2 or 3 or 4. But, okay, that's not going to help me with anything. We need to use a new method I'm going to show you right now called logarithmic differentiation. And the real reason I'm showing you this is by the end of today, we need to be able to find derivatives of other log functions, log base 2, log base 5, whatever, and other exponential functions. And those formulas come from this process I'm about to show you. So, we need to use this method called logarithmic differentiation. We need to use this new method called logarithmic differentiation. Pick up the window and make it a little easier to see. Okay. What we're going to do is we're going to start by taking the natural log of both sides. Take the ln of both sides. And simplify. We're going to take the natural log of both sides and we're going to simplify. So I get the natural log of y equals the natural log of x to the 2x. I took something complicated and made it worse. But there was an advantage to this. There's something we're allowed to do now. Does anyone see it? That you wouldn't have been able to do without the logs there, but because there's a log, I can, do something. Elena? Aha, I can take that power and I can move it out front. I'm going to get the natural log of y equals 2x times the natural log of x. This now looks like something I can deal with. Number 2. I'm going to find the derivative of both sides. And because it's not y equals it's something more complicated, I need to use implicit differentiation. I'm going to differentiate implicitly. So, I'm going to go find the derivative of the natural log of y. And on the other side, I'm going to find the derivative of 2x times the natural log of x. Help me out. What's the derivative of the natural log of y? 1 over y dy dx, because it's something with a y. As for the right side, well, I think that just looks like a product rule problem to me. Go do your product rule. And to me, like first 2x times derivative of the second 1 over x, plus second natural log of x times derivative of the first times 2. I'll clean that up a little. 1 over y dy dx equals, let's see, just 2, I guess, plus 2 ln x. Step 3. I want to solve for dy dx. I want a dy dx formula. And then I somehow want to make sure my answer is just in terms of x. So I'm going to solve for dy dx and give the answer just in terms of x. So of course, how do I solve for dy dx? Oh, I won't. I don't want to do that. I can do something easier. Let's multiply by y. I think that would be a little easier. We're going to get dy dx equals y times 2 plus 2 ln x. But I told you the answer should just have x's in it. The original thing was a function, was an explicit function. I should be able to give an explicit function answer. Any clue what I could do with the y? Elena. We know what y is. Y was, way back in the beginning, x to the 2x. I'll just replace the y with that x to the 2x. This is x to the 2x. We're going to get dy dx equals x to the 2x times 2 plus 2 ln x. That is my derivative. What did I just find? A formula that would give you the slope of the original function anywhere. And all that. These are not going to be terribly pretty looking. That's not really the goal of finding a derivative, though. It's not to simplify something. It's to create a formula that finds the slope. This method is useful in a couple situations, but the ones we're going to focus on are exponential functions where there's a variable in the base and a variable in the power. Those are the ones you're going to have to be able to deal with. Anything so far? We're going to do one more that I think I may lead you through parts of, but you're going to try other parts of on your own. That'll be all we have to do here. In terms of like how important this topic is for the AP exam on a scale of 1 to 10, this is like a 1, but you have to understand this so you can understand the rest of today. So that's why we're spending a moment or two on this. Let's take a look at this one. Let's do y equals the sine of 3x raised to the x squared minus 2. We want to find the derivative. Y equals sine 3x, that thing to the x squared minus 2. We want to find the derivative. Step 1. Remind me, what do I do first? Just say it. Natural log of both sides. Natural log y equals the natural log of the sine of 3x raised to the x squared minus 2. What was the point? Why is that a good thing? that I took the natural log of both sides? Shelly? Gotta be louder, sorry. Yeah, now we can bring that x. That's the whole point. You can't handle something raised to a variable power, but you can handle a product, which is the whole goal of those natural logs. Natural log of y equals x squared minus 2 times the natural log of the sine of 3x. See if you can do your next step of find the derivative of both sides. Don't bother too much with simplifying. We'll do some of that together maybe. Right side, by the way, I think should involve product rule, but also chain rule, because there's something inside your sign. And actually, you know what? The good thing is the left side of these will always be 1 over y dy dx. It's always just the natural log of y on the left. Okay, so first, x squared minus 2 times derivative of the second, 1 over sine 3x. What else with this piece? Okay, so derivative of sine is cosine, so times the cosine of 3x. Honestly, this is a 3-part chain rule problem. Deal with your natural log, deal with your sine, deal with your 3 times. Do you guys see all those pieces? Okay. Next, this will be a little nicer. Second times derivative of the first, how about just 2x times the natural log of the sine of 3x? I will warn you, in general, these get like ugly looking. Whatever. You know what, if I do want to make this a tiny bit nicer, what could I do with that cosine 3x over sine 3x? Why not? Because then it's only one thing to write if I say cotangent rather than cosine and sine. So I'll do that. 1 over y dy dx equals, let's see, x squared minus 2 cotangent 3x. I still have the 3, I'll stick the 3 out front. Plus 2x times the natural log of the sine of 3x. Multiply both sides by y. Am I good and done? Do I need to shut the window in the back as well? Is it? Yeah. Sorry about that. Yep. Yeah, that might be a little easier to see. I'm done. Am I actually done though with this problem? No, I'm done with this year, not done with this problem. Oh, what do we do? Yeah, replace the y with the mess that it was in the beginning. This is the sine of 3x. Raised to the x squared minus 2 times 3 times, well, I don't have to read this. You can just copy from the line before. And we're going to get that. Maybe. I'm getting a bad look over there. What did I do wrong? Am I right? Is this? This is logarithmic differentiation. Again, yes? Oh goodness. Okay. This is logarithmic differentiation. I think there's like 3 or 4 in the homework. You're messy, but it's the same idea every time. Take the natural log, move the power up front. Before we go out for our math break, I want to do one other thing quickly. The rest of today is about other exponential and other logarithmic functions. In your packet of stuff I gave you, there should be a sheet that says pre-calc review. of exponential and logarithmic functions. I want to very quickly go through that. Then we'll do our math break. Then we'll do derivatives and integrals, which honestly are just going to be some more formulas that you know. So it shouldn't be horrible. But I'm looking for the sheet that looks like this. Pre-calc review, exponential and logarithmic functions. By the way, don't be looking in the stuff I gave you today. This is the end. You're just going to follow along. Exponential functions at y equals 2 to the x, y equals 10 to the x, y equals 1/2 to the, you've been working with these since like algebra 1. Logarithmic functions are the inverses. You've been working with these since algebra 2. Y equals log base 2 of x, y equals log base 10 of x, y equals log base 1/2 of x. You've seen things like this. You should know the basic shapes of the graphs. We're not going to do any graphing. You did lots of that the last 2 years. Exponential functions that have this basic shape. Logarithmic functions are their inverses with that basic shape. There are two main things we've got to be able to do. We need to be able to evaluate logarithmic expressions, and we need to be able to solve some equations. Properties of these things. First thing, we have our inverse property, which is probably how you started this thing in algebra 2. 2 to the third equals 8 has the same basic, I don't want to say same basic meaning, but is the same idea, kind of, as log base 2 of 8 equals 3. The way I talk about this in algebra 2, logarithms ask the question, what's the power? So log base 2 of 8 is asking the question, 2 raised to what power gives you 8? And you know the answer is 3. This one over here, log base 81 of 1/9 equals -1/2. 81 to what power gives you 1/9? Well, it's actually not a power, it's a root, square root. Not just a square root, but 1 over a square root. How do you show that as a power? -1/2. Hopefully this is coming back from the last couple of years. I want you to evaluate some logarithms. They're all asking what's the power. Oh, wait a minute. Did I mess up in number 1? I forgot to put a base. If I don't write a base, it's base 10. We call that the common logarithm, although as far as calculus goes, it's no more special than like base 8, base 7. E is really the special base. But take a moment, see if you can evaluate these. They're all asking the question, what is the power? The base to what power gives you the number inside. If you need to rewrite some of these, like the first one as 10 to something equals 100, that's also how I would have done this in algebra 2. Might be helpful. And I will be calling on you people to give me some exponents in just a moment. Well, not you people listening at home over break, but the people who are in front of me. I'm just going to do the first one. Log base 10 of 100 is 2. 10 to what power gives you 100? 2. Lauren, what do you have for number 2? Yeah, 4 to what power gives you 16? 2. I like it. Josh, what about 3? 5 to what power gives you 125? 3. Good. Bradley, what about 4? 1. Log base 9 of 9 is 1. 9 to what power gives you 9? 1. As long as it's the same base and same thing inside, you're getting 1. Kendall, what about 5? 0. Anytime there's a 1 inside your log, you're getting 0. 8 to the 0 will give you 1. Nate, what about 6? Negative 3. If you want to move it to the bottom of a fraction, you got to have a negative exponent. 2 to the third gives you 8, but on the bottom of a fraction will have to be negative 3. Ellie, what about 7? Negative 1. Sure, 3 to the first gives you 3. Move it to the bottom of the fraction by making it negative 1. Victor, what about 8? 1/2. You're not really doing a power, you're really doing a root. What power means? The square root, 1/2 power. Clara, what about 9? 1/4. You're doing a 4th root there to get that. And finally, Abby, what about number 10? You're doing a square root, and you're moving it to the bottom of a fraction, negative 1/2. I'm pretty sure in the homework there are like 8 of these. That should probably take you 30, 40 seconds or something. You've been doing these for a while. I know when I teach these in Algebra 2, they find these really, really easy. And it's been a couple of years since then. Okay. Any questions or issues though? The whole point is these things are inverses. Exponential functions and logarithmic functions are inverses. So if you put if you put an exponential function inside a log, the log and the exponential, they cancel. If you put a log in the exponent of an exponential function, the exponential and the log, they cancel. You're just going to get an x out of that. You learned the change of base formula back in Algebra 2. How to evaluate logs on the calculator if you don't have that like log base anything button. If I want to figure out log base 8 of 15, you could have done on the calculator log base 10 of 15 divided by log base 10 of 8. Because you got a log base 10 button. But actually, this works for rewriting a log in terms of a log with any other base. As far as calculus is concerned, natural logs are the most useful for us. I can do this problem by typing in natural log 15 divided by natural log 8. And you'll get that decimal. Log base 2 of 50, I can type this in on the calculator as natural log 50 divided by natural log 2 and get that decimal. Turn the page. We're going to solve some equations. There are 2 ways we can do the first one. If we try to use our inverse property, I would take the log base 5 of both sides. I'll show you the way I do this in Algebra 2 though in a moment, and I don't really care which method you use. If I'm using my inverse property, I'm going to take the log base 5 of both sides, just like to undo an e to the something, you would take the natural log of both sides, I'd take the log base 5 of both sides. Because the point is, because they're inverses, they cancel over here, giving me x minus 3 equals log base 5 of 3,125. The way I would have explained this in Algebra 2 is, let's take this exponential problem, rewrite it in log form. I would say log base 5 of 3,125 equals x minus 3. I really don't care how you do it as long as you can get down to something like this. Please take out your calculators. And I want you to use that that change of base formula, but let's try it with natural logs to evaluate this thing. You're going to type in natural log 3,125 and make sure you're then closing your parentheses, divided by the natural log of 5. Oh, I wasn't expecting that, but it's a nice number. Are you getting something nice? Like a 5? Don't expect that in the homework necessarily. There probably will be decimals. Totally fine. X minus 3. Oh, this is really easy now. What's x? X equals 8. Next one. To undo a log base 3, we could do 3 raised to both sides if you want to try to use your inverse properties. If you don't care about using the inverse properties and just want to think like Algebra 2, you could convert to exponential form and just say 3 to the 4th. equals the thing inside there, which is what this will become. 3 to the 4th equals the thing inside there. You should not be using your change base formula here. 3 to the 4th, not ln 4 divided by ln 3, truly. 3 times 3 times 3 times 3. Times, I don't know how many I said. Whatever. I'm getting 43. I am going to stop recording, and we're going to take a math break.